Great. Let me select the PDF file.
And then I will hide myself because I'm not the point anymore.
Okay. Let me see how I can control it. Previous slides. You know I can control the PDF. I'm not entirely sure how to change the slides. Let me just screen share. I think it'd be easier. Okay, everything good? Do you see the slides and everything? I guess so. Perfect. All right. Well, hi. My name is Federico Pizzuti. Present my work with my two supervisors, Michel Stueyer and Christophe Dubach. And we're going to talk about generating high-performance code for irregular data structures using dependent types. So I'm in the business of data parallel functional languages. These are languages that try to answer the problem of programmingly parallel heterogeneous hardware, which is quite a difficult task. The idea is that we're going to use the properties of functional languages, so the high-level nature of them, plus the correctness guarantees and the ability to generate efficient code. And we use this sort of system extensively for what we call regular data applications that work over relatively regularly shaped data. However, irregular and sparse data structures are not just as well supported as the first use case. The goal for this talk is to show how can we provide a basis for the first-class expression of such sparse and irregular applications. And we're going to kind of build up from the basics up to the desired level. So the setting of these languages, again, how they work, we tend to use types to represent the shapes of data structures. We use algorithmic patterns to express data transformations. And then we use kind of algebraic reasoning to express, through rewrite rules, optimizations. And these are the ingredients that hopefully will give us a compiler which can generate optimized parallel code for sort of GPU targets, for example, in our use case, but it could be other targets, your kind of low-level parallel target. In this talk, we will focus on types. The rest is kind of in the background. It's still there. In fact, our goal is to extend our type system to leverage the machinery that is already there. But we will not talk about compiler details per se, more like type levels. So we start with the most basic type, the type of a regular array. And that's the notation we use. I'll explain it very shortly. So n is the length of an array known at the type level. Delta is the element type of this construction. We can nest arrays together because arrays are themselves data types. The reading is kind of right associative. So n.m.delta means n arrays, n sort of outer arrays of m of delta. So 3.5.float32 would be an array of 3 arrays of float32s, each inner array length 5. This kind of array types can be used to describe the semantics of many of the common data parallel patterns. For example, in a map type, we could say we take a function from t to u, and we take an array of n.t and a return array of n.u. So we're not going to change the number of elements because we're mapping. While in a reduction, for example, we're going to shrink the array down to an element. And we can also model other type of primitives, such as split and join, would say reorder the elements in an array. So we can say, give a certain length, I can try to split the array, group things. So these array types are very rich and allow to talk about these problems we care about. And they can be used again for many applications. Linear algebra is one of such examples, but also stencils, such as convolutions, acoustic simulations, image processing, such as filters. All this work over grids, and this works very well. Just give an example for this talk. We kind of run through this example. It's the sparse matrix vector multiplication. So given a matrix and a vector, we write a functional program, which looks sort of like this. We have some inputs of which we give types because we need to specify the shapes of our data. And then we use some standard functional notation. We use this reverse function application for like simplicity, but that's nothing new. The compiler of this data parallel functional language then can use all this information to generate quote-unquote efficient low-level code. Now, in this talk, we'll not talk about parallelism. We only talk about other concerns, so I'll just show sequential C. But even in this sequential C, we notice that the loop bounds have been inferred from the types. the loops, the map and reduce loop, have been fused together, so we can do this kind of optimizations. And also the matrix, which is a two-dimensional array within our kind of type system and logically, is actually implemented as a flat buffer. And the array can figure out the flattened indexing thanks to the kind of algebraic properties of what does it mean to index into an n.m.flow32. However, we have a limitation. The shape must be regular. The types can only represent rectangular grids, and no amount of nesting these arrays can ever give us anything more. But what about other shapes? For example, triangular matrices. Well, we need to generalize the type a little bit. We say we still have an array, which is like an and dot something, but instead of having a single sort of type, we have a sort of a function. Actually, more like a lambda, right? We're scoping the index. This I ranges from 0 up to n-1. So I kind of takes the value of every of the index for every single element, the next index. And the actual kind of the element type is going to be dependent on I. So we can think of it as a function of I. So this f is a kind of a function from natural number to type. In fact, the whole body of this array is actually a type level function that takes a nat and returns a different data type. For example, again, the triangle example, we could say there is a triangle whose height is 5, so we can have an outer array of size 5, and then the inner size is I plus 1, so an array of I plus 1 floats, where I is the index of the array. How do we use it? This is position-dependent arrays. Very much the same. We have to, of course, update the type. So, for example, if we're doing a sparse matrix vector multiplication, we change the type of our matrix to use this new formulation. But we pretty much leave the rest untouched. And now the compiler, again, this data parallel compiler, can generate efficient code, which very much resembles the other one, of course, with some interesting things. For example, now the inner loop is limited to the outer loop, because now we have this kind of dependence. And also, the matrix is still a flat buffer, and the compiler can figure out a closed form formula, because in general, indexing into this kind of position-dependent array could be arbitrarily complicated. You might have to run a loop to figure out your index. But the compiler can figure out that actually there is a closed form formula. And this is very similar to polyhedral kind of optimizations, that kind of space. You just figure out what the formula is from the algebra. Okay, but now we want to talk about irregular applications and sparse data. So let's talk about CSR matrices, which can be a very good example. So a CSR matrix is a sparse matrix. So we have a logical idea of a matrix, but in actuality, we store it in a compressed way. So instead of having just the values, which are the non-zero values array at the bottom of the slide, we also have row offsets, which is kind of metadata that gives us the structure of the matrix. Each row, the length of each row is the difference between the offsets, the start and end offset. And also we have column indices that help us reconstruct the structure, because for each row, we need to know where in the column a value is. So what if we wanted to express this kind of shape with the types we currently have? Well, it's going to be a matrix. So we have an outer matrix dimension. There's going to be some kind of position-dependent array. We know that much. We know the element type. We can kind of zip the column index and the values together. So we can say we're going to have the float, which is the non-zero value, and some index bounded up to m, which is the kind of column index, because it's never going to go over m, so the column of the matrix. But what can we put there, right? It's kind of, how do we express this? So the problem here is that our position-dependent arrays cannot talk about values, sort of cannot refer to other values. They can only play around with the index, but they cannot introduce dynamicity. Now, in order to introduce dynamicity, we need to introduce a new concept. So let's take a step back. So far, we talked about this kind of natural numbers, and we call them nuts. These are type-level natural number expressions. We use them in array sizes, array indices. Everywhere you see a number at the type level, it's a nut. However, we can extend this with the concept of nuts. So a nut is an index sequence of natural numbers. So it's fundamentally an array at the type level of nut. Given a nut, you can index it at a given nut to get the nut at that index. So you can also think of it as a function from nut to nut. But it's kind of a reified function. We want to really convey it's kind of an array. And now, if we had such a nut of offsets, so a nut called offsets, which contains the matrix offsets, we can now write the type, because we can have the outer matrix dimension like before, and now we can have the inner matrix being this expression. So saying, look at the two offsets, as we said, because the two offsets, like the difference between the two offsets gives you the row length. So this actually, we can talk about it. And now we can actually talk about the value is the same as before. So it's a float and the index. So kind of to give a visualization, you can think of it, the offsets is just kind of an array in memory, but somehow referable to as the type level. And the data itself is just the sparse matrix, which contains the value packed together with the column index. So how are we going to get our hands on one of these nuts? Well, we can introduce these two primitives, lift nut and lift nuts. What do they do? A bit clear now. So given a value level expression of type either integer or array of integer, we can freeze it and lift it to the type level for some inner scope. So in some inner scope here, kind of expressed as an argument function, the value of that expression can be kind of bound to the type level variable. And then we can compute something, and then we can return the value, which does not depend on the nut and the nuts, because they're not named. So you can use it, but it cannot kind of appear in the type T. And so this is safe. So we can compute and go away. To make a very simple, silly example of this, we could say, given two arrays of integers, A and B, we could sum up the values of A, so reduce the value of A's, and then kind of the result of that reduction, make it a type level construct called count, use it to take some elements out of B, because take wants to know how many elements it wants, because all arrays have known sizes, and then reduce B again. So if we look at the generate C code, the point is that count is both produced by some user code in the reduction and in the type level kind of expressions for the second loop. So now we have a way to link together dynamic values and types. Okay, so how do we deal with this CSR matrix? Well, let's create a function. Let's assume somehow we created this offsets with this lift business. And now we can take a matrix and a vector, and that's it. We don't really need to use offsets because it's only a type level construct. We just need it to scope it. We just need to scope it to refer to it. And the compiler again can now generate the sparse matrix vector multiplication. And as we can see in the generated code, we're going to refer to the indices in these other data structures. So we're actually going to fish out the indexes dynamically, right? Because these offsets could be computed, and this matrix is basically an input data. And also, once again, the index has been kind of flattened. And very interestingly, the compiler realized that doing the kind of the summation over all these different lengths is actually just looking up the last offset. So the compiler basically figures out why we want CSR matrices in the first place, which give us fast kind of random access in the middle of the matrix, which we need for parallelization fundamentally. Very good. We now can produce these kind of structures. But now we kind of have a problem. What we want to write another program. We want to write the program dense to CSR that takes a dense matrix and generates a sparse matrix. What would the type of this program be? Well, let's say we take a dense matrix, which, as we saw before, it's an n.m.float32. That's fine. And then let's write the return type, which we just give for a sparse matrix. And now we have a problem. This offsets is somehow leaking out of the body of dense to CSR, because ideally, offsets is computed from the matrix, right? It's kind of with this lift nuts, we're going to generate it, and then we're going to use it, and now we want to return something, but now we have like an unbound variable out of our function, and we need to call the plumber because we cannot leak variables in the scope. So what are we going to do? Well, first off, we must realize that this is not the program we're looking for. Absolutely not. This is the program we're looking for. We take a dense matrix, and we're going to return both offsets and a sparse matrix. In order to look at the sparse matrix, you need to have the offsets. You cannot make sense out of it. And so it's not really a symmetrical pair here. They're not equally good, these two values. The first one is necessary for the second one. So we cannot express this construction currently in our language. We cannot say these two elements, pack them together, and introduce this dependence. We cannot create enough. We cannot do anything. But as people know dependent typing would know, there is a solution to this problem. It's called dependent pairs, which is what we introduced to the language. So what is a dependent pair? Well, it's a pair. So it's made of two things. There is a named first element, and the name is kind of a type. This is type, right? Where we're talking not the value, we're talking about the type. So the type is named, and the first element can only be, for in our use case, either a nut or a nuts. We don't care about having kind of generic dependent types, because that would be really hard to compile efficiently to a GPU. So for now, we just restrict what we know. Name first element, and then the second element, the type, is dependent on n. And again, we use this formulation where the type is basically a function of n to talk about a type which is dependent on n. For example, so in many languages, arrays have kind of dynamic size, right? You kind of represent them by writing the size as a kind of a header and then the body of the array. And so far, we couldn't do this in our language because our array sizes are kind of only known at compile time because we want to elide it away. But if you wanted to have this level of dynamicity, now you can, because you can say fundamentally you have a dependent pair whose first element is not n, and the second element is an array whose length is n. So now we can actually express a sort of dynamic array whose length is kind of encoded within the value itself. How do you construct a dependent pair? Well, given if you give two things, so if you give, say, a nut and something who depends on that nut, we can package them together and sort of record the dependence. This recording is done from the fact that this I turns into n. It's just kind of standard trick. Now it's independent, right? It's kind of encapsulated. And how are we going to access it is a bit more complicated because, of course, we cannot give first and second projections because second projection would make no sense. Again, you need the first thing to look at the second. So we're going to give you something called match, where you take the whole pair and you pass in a function who takes the two values separately. And now we can use kind of dependent functions to express the fact that the second argument must depend on the first, right? And then they compute some type t, which again does not refer to I in this case. It cannot refer to I. And once we return, we're done, and there is no more dependence. And if you want to kind of carry around the dependence, T itself would have to be a dependent pair, right? You can match it apart, do some computation, and put it back together. So that's the kind of setup where we use dependent pairs. And now with dependent pairs, we can actually give a proper type to our CSR matrix, because we can say that the CSR matrix of size nm is actually, oops, sorry, my bad, mouse scroll, is actually a dependent pair where the first element is the array of offsets, which is a nuts, right? And the second element is the kind of the data in a column indices who depend on off, using the formula we saw before. And now this is a self-contained item, right? There is no dependence anymore outside this bundle, which means that we can write dense to CSR. We can take a dense matrix and generate a sparse matrix. This is not only for sparse matrices. You can represent, of course, other data structures. Graphs are commonly represented in a similar way, where you have a kind of array of offsets, which kind of defines slices. And then for each node, you have a slice, and the slice has the index of the nodes this node is connected to. So each edge is kind of implemented with this two-level way. And once again, we can just use the same structure and use a different element type. Instead of having the float and the index, we just have the index. So we only care about the node address. So how are we going to evaluate the kind of, this is still functional high performance computing. This is high performance. So for now, we show the results of evaluating dense CSR and sparse matrix multiplication, the implementations we give in the paper. Our compiler generates OpenCL code, so it targets GPUs. In particular, I've been executing on my NVIDIA 1080 GTX that I have on my desktop computer. The reference implementation is the NVIDIA cuSparse sparse linear algebra library. So it's kind of a state-of-the-art linear algebra library that actually uses CUDA and is kind of native for the GPU. All the graphs I'm going to show you give speed up related to cuSparse. So all numbers are kind of on the baseline of cuSparse. So the first evaluation is the dense to CSR. So on the x-axis, we have the matrix dimension. And on the y-axis, we have the speed up, because again, we give relative speed up. And these are for different matrix densities. So different matrix densities change the performance characteristic of the program significantly. And we can see that in most cases, we're quite faster than cuSparse, 1.5x, 1.2x, some cases even more. We suffer a bit on the dense matrix side, but nothing can be perfect. Still, very competitive with cuSparse. And the second one is the SPMV. SPMV, sparse matrix vector multiplication. On the x-axis, we have a set of kind of commonly used matrices, sparse matrices throughout the literature. Many papers use this, so I kind of sampled from them. And once again, we can see we have speed up, we have a mean speed up with sparse, and in general, we are competitive. So yes, so basically this approach allows us to be competitive. Now, I want to stress one thing. This is not because of the types. The types didn't make our programs go fast, right? The types only allowed us to leverage the machinery of data parallel functional languages, which has been built kind of over a decade by kind of the community of research. It's kind of a low-hanging fruit here, right? We're working on the expression size to kind of leverage what the machinery already can do. So the talk I gave here kind of covered several years of work, kind of gave you a vertical slice of the work. Started for me at least when working on Lift, so ICFP 15 paper, where I introduced the system with irregular arrays and that sort of setup. I generalized this to the static position dependence, so the triangle stuff, which was presented actually at FHPNC in 2019. The idea of using a dynamic value to be able to express sparse matrices comes from CC20. And then in this kind of paper, we extended it by providing dependent pairs, providing the lifting, and in general, doing a makeup of the whole system to make it all kind of work together nicely and formally. And also, we combined it all together to be able to support this kind of sparse application on both sides. So now you can compute, you can consume sparse data structures like sparse matrix vector, and you can produce sparse data structures. So you kind of have the full picture in a sense. Of course, there is much more in the paper. We talk about the type system in great detail. We give there were three case studies, dense to CSR, the sparse matrix vector multiplication, but also the breadth first search over the graph, which didn't make it for the presentation, but it's all in there. We also talk about code generation and optimization, and there is some detailed performance analysis. And actually, that's my presentation, so I'm happy to go and take questions or anything else. Oops, I will.
Yes, and I don't. Where is the applause button? I don't know.
Well, thank you very much.
Yeah, great.
Plenty of emojis. I feel very happy.
Yes, and there's also a bunch of questions. And you can people can still go in and ask questions in the QA tab to the right of the video stream, and you can upvote questions, and I'll post the questions in the upvote order. So I'll start with this one, so do you rely on later phases of the compiler optimizing the add and multiply into FMA, or can this be done at MapReduce fusion time?
Sure, what FMA do you mean?
Fuse, multiply, add.
Okay, no. So the way it's done, it's basically the compilers. So this is explained better in a paper we could publish about the compiler architecture. But the general idea is that all our primitives are kind of lazy and then there is a kind of a whole system machinery to kind of generate values in a pool-based fashion. So the map basically doesn't do anything; it just kind of wraps around, and then when you go generate the code of the reduction, right? You kind of wrap around, and then ultimately you're going to generate the output value of the program. And as you walk back, okay, what did it take to generate the output? Okay, the last thing, so on and so forth. It kind of starts pulling out values and kind of introducing copies where necessary. Yeah, you specify where to introduce copies. So in general, everything is fused directly. So it's basically a later phase of the compiler, but not really optimization. Is like the actual structure of the compiler. Like everything works like this in this compiler. There is no way around it. I hope this answers the question. I'm not sure. We can expand later if necessary.
Well, I'll mark it as answered. So the next question is, does the compiler rely on or take advantage of types during optimization, or are types only used for verification?
Extensively. That's basically the optimization come out of this system. Basically, all the information the compiler has is through types, and any sort of optimization is through types. Now, some of the optimization is really fundamental. Like I showed you when you are accessing a position-dependent array, we are, in a sense, inferring the flat closed form formula. This is technically an optimization, right? But it's kind of a necessary optimization. Without this would be unbearably slow. But there are also other optimizations, of course, that take advantage of these types. But a lot of them are in the algebraic space. Like we can prove things are equal and kind of remove operations, or inline loops that we know, of course, they have a fixed size and stuff like that. I mean, the standard gamut of optimization. So yes, very much so.
Okay, nice presentation. I agree. is there any strong reason to have a NAT type separate from arrays of indices? We were thinking of implementing something similar, but we're planning to use arrays that are in scope as sources of sizes for other arrays.
Yes, the main reason for this is to kind of keep it manageable, because if you allow an expression to be inside your type, right? If you say, okay, now I can put an expression whose type is array of index inside my type. Well, now I can put map of something inside my type, and I can have map reduce something inside my type. I can have a crazy program, right, that does something insane inside my type. So this is technically okay, right? There is nothing fundamentally preventing you this, but I found this to be very hard on the implementation side. So the idea of saying you first compute it and then you lift it, and at any moment types are types, values are values, and the link up point is just this lift nut. So it's more of a strategy for the compiler writer. There are, of course, alternative formulations where you could imagine that you just inline the program within the type, and then you kind of do this kind of pulling it apart kind of mechanically. This was something we presented in another paper. Did this just for clarity? I think it's cleaner to express it in this other way. But yeah, sure, you could do it.
All right. So now here come my questions. So could similarly fast code be written with data parallel functional programming without dependent types by implementing the code with flat arrays with manual offset computations, which is presumably what your compiler does as an intermediate step anyway? I
think so, yes. I mean, we live on a space, right? On one hand, there is a C where you like do everything manually. And on the other hand, there is like this stuff where you try to kind of keep up the illusion of, oh, it's actually a matrix, it's two-dimensional, we map over it, we fold over it, and stuff like that. And then, of course, there's something in between where you could say, actually, it's a multi-dimensional array, but it's actually an array. You actually pull out indices, kind of a bit like what single assignment C does, I think, right? It's kind of like you have a multi-dimensional arrays, but then you pull out indices and you do manual indexing. You could do that, of course. And another thing to point out, however, is that we're working in a parallel context, and there is a point where this interfaces with the rest of the language, right? So we want our parallelism to be in our map. So the thing you want to be parallel over needs to be an array dimension, because you need to map over it to know how much to parallelism. So if you do this kind of system where mapping tells you basically everything about the parallelism, then I think, and if you want to map in parallel over a sparse data structure, then I think you might end up in the same place. But sure, nothing stops you from doing something like that, of course.
So do you have an idea of how much? Presumably the program that does this manually would be larger and uglier?
Would be larger, yes, uglier. I mean, beauty is subjective, but possibly. But one thing I can tell you, it will be more error prone. That's for sure.
Right. Okay, then we have a question from Jeremy. NAT lifting is a kind of existential quantification?
I think so. So the idea here is, yeah, I think so, basically. I think you're saying in that scope, there exists, yeah, I think it's a form of existential quantification. I mean, this stuff really interfaces with dependent pairs, right, which are kind of existentially types. So yes, as far as my understanding goes, this is a form of existential quantification.
All right. And then another question from me. Mm-hmm. So does the type checker provide any guidance on when the compiler is able to turn indexing into closed forms?
Well, it will shout at you if it can't. It will tell you, look, I cannot do it. I will generate a for loop for every access you do, which is going to make your program 10,000 times slower on average on a GPU, because now there's no more parallelism. But the reality is, unfortunately, I don't think we have a good enough theory for understanding when things are simplifiable and giving good feedback on when they're not simplifiable. I think my supervisor, Michel Steuer, is actually kind of musing on someday having something like this, to actually have a stronger language to talk about how to deal with these arithmetic expressions, with nuts. But right now, no. Right now it's very much like it's put in a simplifier. The simplifier simplifies good. Otherwise, well, you look. The good thing I would say, in my defense, I would say that the programs you want to do, right, with data parallel languages are going to be data parallel. And if they're data parallel, the simplification must exist. It's like it's a fact of reality. If it's parallel, it means you have a closed form formula. And if you can't have a closed form formula, well, you're trying to do something sequential. I can't do that. But yeah, sure.
Okay, that was the last question in the Q&A panel. Does anyone else have any final questions? It seems not. Then let us give our speaker another virtual applause.
Thank you very much. The best applause I ever received.
Yes, great talk. So I'm going to kick you off stage.
Yep.
And now it was pointed out to me that we started a bit too early with this first presentation, which is not great because it means we don't follow the scheduled program. So now we're going to take a very small 7-minute break so that we will be on track. We will be following the schedule with the next presentation. So go and get a cup of coffee or stretch your legs very briefly. Only 7 minutes. So.